Welcome everyone to the first Livino Data Science seminar of the 25-26 academic year. So really happy today to be joined by Dr. Carol Cuesta-Lazaro, who was at the MIT and Harvard, but has now just told me that she's moving to New York, where she's a research scientist at the Flatiron Institute at the CCA, and is also a member of the Institute for Advanced Studies. So Carol is going to talk to us today about Build Big meets Build Smart to explore the universe. So whenever you're ready, please feel free to get us away.
Thank you very much, Alex. First of all, I'm very happy to be here. I met Alex through the CDT program. I was a CDT student at Durham a few years ago, and I really enjoyed the freedom of the CDT. So you see many of the things I've worked on started through the CDT and then have developed into my research program today. So yeah, super happy to be here today. Also, if we can make this as interesting as possible, that'd be great. It's okay if I don't get to the end of the talk. That's not the goal. So feel free to raise your hand and let me know if you have any questions or comments or something you'd like to hear more about. But the goal today was to give you a sense of the kind of things I'm working on in cosmology, but hopefully these are more general ideas that are useful intersections between machine learning and science. But first, I wanted to tell you a bit more about why I am particularly excited about the next few years in cosmology and astrophysics. And it is because we're going to get a lot of new data, right, that we haven't seen before, from all different wavelengths and probes that are probing very different aspects of the universe. So here you have a few examples. I've worked a lot on galaxy surveys, at DESI in particular, so 3D point clouds of galaxies, and we will talk more in depth about them. But in general, there is a lot of data coming in, and we call this like the era of big data cosmology. Now, I think if we were to be fully honest, we should call it the era of big one-dimensional data cosmology, right? Because we don't actually analyze these like beautiful high-dimensional data sets that I had before, but one-dimensional summary statistics of them, usually handcrafted summary statistics. So if we look at galaxy clustering or gravitational lensing, usually we compute two-point functions like correlation functions, power spectra of the data. So we summarize these high-dimensional observables, let's say millions galaxy positions, into 100 data points. That tells us how they're correlated on large scales. And we throw away the rest of the data. Right? So what we're going to argue about is that machine learning can help us not do that, right? So avoid these like lossy compressions of data sets and look at the data in a more holistic way. Now, if we want to do that, there's something we have to be careful about, and it's the astrophysics involved in all of these probes. In cosmology, usually we refer to astrophysics as the nuisance parameters that we want to marginalize over. But I think it's going to require a bit more care about what's happening on a small scale if we want to really do this at scale. Now, what are the questions that I'm interested in particular? Well, it's things that are actually very hard to probe, like what is dark matter made of, right? So we know there is 5 times more matter than the one we can see, and the bullet cluster is one beautiful picture that summarizes this into when you have two clusters colliding, you see the matter just went past through each other, collisionless dark matter versus the gas interacting in the middle. Most recently, we had some new evidence on dark energy, possibly. So there's still very early days, but DESI, this galaxy clustering collaboration, has been measuring whether dark energy might be evolving with time. So far, we were very happy with the idea of a cosmological constant, so dark energy, which is constant as a function of time. But there's a measurement from DESI where they parameterize how dark energy might be evolving with time, some sort of Taylor expansion. So here, lambda CDM, so cosmological constant, will fall under this point here. So the 0 - 1 point. But we see that there's some hints or small evidence that this might not be true. Now, it is still very debatable whether it is actually there or not. So time will tell once we have more data and a better handle of different surveys and what's happening. We will see whether this is actually a true signal, but there is some interesting thinking about whether dark energy might be evolving with time, which is very exciting, right? Because so far, a cosmological constant was able to fit everything we could see. And finally, we definitely want to learn more about the early universe. So inflation is still our paradigm of how the universe actually kind of came to be in terms of how density fluctuations even started in the very early universe, but we know very little about its actual characteristics. And it's been very, very hard to characterize it because the only data set we had so far was the cosmic microwave background, so this picture here, But now galaxy surveys are becoming also an interesting way to probe the early universe, but also other probes like gravitational waves, etc. So it's a very exciting time to think more about the very early universe because we're starting to be able to probe it in very interesting ways. So these are the big questions. Now, if we go back to Earth, we can see that probabilistic machine learning has advanced a lot in the past few years. And this is one of my favorite examples showing how ML really has made high-dimensional inference tractable. And this is called Genie-2. It's a model that can generate playable worlds given a textual prompt. So here you see an example of a human actually playing the world that was generated by the AI with only a sentence of text. And you can see the diversity of worlds that were generated by this model. Now, this was made 6 months ago in 2024. So obviously in machine learning times, that means it's extremely outdated. There is already a new version of Genie called Genie-3 that is even much better. Now you can play in real time. So the previous example actually wasn't playing in real time, but now you can. And you can see that the resolution has improved massively. And it's not just resolution, but the physical consistency of the world is much, much better. Like if you come back to the same spot, it will actually look the same. Whereas that wasn't true for Genie-2. So these models are just trained at scale, right? That there isn't anything smart being done to them to just generate a world given a textual prompt. So extremely high dimensional inference, if you think about the number of pixels that are being generated, let's say this images might be 1,000 times 1,000 pixels, and then you have the time dimension as well. So extremely high dimensional, and then you still have to learn the correlation with text. So it's a very hard problem. Now, of course, this has also had applications to the sciences. So an interesting application of generative models in science has been drug development, where you want to develop a drug given some properties. I think this is a very interesting problem because you can actually tie this up with a wet lab that actually synthesizes the drug in an automated way sometimes. Like this is the way people are thinking, right? You can automate the full process, and then you can still give feedback to the model when it made mistakes, right? So the idea is that these models are not going to be perfect, but they really do like make the search space much more tractable. So before it was extremely expensive to synthesize all the drugs that we thought could fulfill these properties, but now we have a much more restricted search space that we can actually make tractable when we synthesize it in the lab and still feed back to the model. Now, applications like this are difficult to come up with in astrophysics, where your model is allowed to be imperfect, but still extremely helpful. But I would say we need to think more in these terms. It's rare that models are going to be perfect. They'll always make mistakes. Now, they don't need to be perfect. They need to be very useful for them to be able to change the way we do science. Now, why do I think this is a good time to put these things together to answer the questions that I told you about? What is dark matter made of? What is driving the excited expansion? And how can we learn about the early universe? Well, because these three things are actually coming together at the right time. So in terms of compute and simulations, these are getting way better and more sophisticated, but ML can help us bridge the huge data sets, high quality data sets that we're going to be getting over the next few years with this compute and simulations so that we can solve interesting inference problems. But I would like you to think more about them, not just as tools, but a new way of thinking about physics and how it ties up with like simulations, for instance. So usually you want to think about how can I frame my problem as an optimization problem or a problem in which I learn a useful representations about the underlying physics. Now, my background is pretty varied. So I've worked in a lot of different problems, and it actually started with a CDT, right? So you had to do some industry placements. I worked on epidemiological simulations, for instance, but also like natural language processing, Amazon. So I would really encourage you to take advantage of the flexibility of the CDT to really work on broad problems during your PhD and then find what you really are interested about. In particular, if you want to learn about machine learning, industry tends to be actually a better place to learn about it than academia, I would say, given that the expertise is really more there. So I learned a lot from them, then came back and continued working on it in astrophysics. And here there's some examples I were trying to highlight this intersection. In particular, these symmetry preserving machine learning architectures, I think, are a good example of work at the intersection where as scientists, we care about symmetries, and actually they end up being helpful more generally in machine learning because they allow you to build architectures that are much more data efficient, for instance. But you really needed people at this intersection to come up with them. And I'm sure more things will come out of this conglomerate of physics, statistics, and compute. Now, what am I going to talk about today? So I wanted to highlight these three different problems. Let's see if we can get through all three. But these are basically three themes. One on how do we build fast simulators of our simulations, but we can also use them as likelihood models, so to do inference, the same model, in particular for galaxy surveys, but more generally. I'll talk about an interesting problem of whether we can actually run the clock backwards. So, okay, we see the galaxies today, but can we say something about how the very early universe looked like? And machine learning can help us do this because it's an extremely high dimensional problem. And finally, I'll talk a bit about hypothesis generation and how we can perhaps use language models to learn something interesting about the universe. And what's the status in that direction? Okay, so let's start with how things are being done at the moment in cosmology. So usually you have some theory parameters, theta, that you want to quantify. These are describing the overall composition of the universe. So what is the density of dark matter? Were dark energies evolving with time or not? Some parameters that constrain the physics of inflation in the early universe. So these describe the overall composition of the universe. Then you have the forward model, most usually perturbation theory in current generation of galaxy surveys. So basically you tailor expand gravity because on large scales is weak, so we can actually tailor expand it. And we make some predictions about lower dimensional summary statistics of our data set. So this is an example of a two-point correlation function. So how likely it is to find a pair of galaxies at any given pair separation. So a large scale summary statistic of your millions of galaxies point cloud. Now, what we want to do is solve the inverse problem, right? So we want to go from our measurement, or observable, in this case, with order 10 to 100 data points, the two-point correlation function, to our physical constraints, so to the posterior over those parameters. Now, posteriors are extremely important in cosmology because we want to make sure that given that we only have one universe to make claims about, that we know whether our claims are statistically significant or not. And the evolving dark energy is a good example because, okay, the model does prefer evolving dark energy, but actually it's not very statistically significant. You can see that is about 3 sigma deviations from lambda to the m. So it's not super significant, in particular, given all the systematics that need to be taken into account. So you really want to go definitely higher than 5 sigma to make a discovery, but possibly more in cosmology. Okay, we really care about posterior, so that's going to be a theme as well today. Like quantifying uncertainty is extremely important for cosmology, in particular because we only have one universe. Now, what I've been working on is on replacing these perturbation theory models by simulations, so fully nonlinear simulations, so that we don't have to restrict ourselves to the very large scales of the universe, but we can try and use most of our data. And to avoid the summary statistics. So instead of summarizing data in this like 10 to 100 handcrafted summary statistics, can we actually make use of the raw data using machine learning? And can we do, well, first of all, because we hope that this will allow us to constrain these parameters much better and make these maybe tensions more statistically significant. Now, this is my very optimistic forecast because that's where I would like the universe to look like, right? I think it'd be more interesting if dark energy was actually evolving with time, but obviously this is completely made up, so I have no no data to back this up. It could completely be consistent with lambda CDM. We don't know yet. And what I hope is that we can go beyond just constraining the average properties of the universe and infer things like the initial conditions. Like, can we infer the random seed of our universe to learn something about how the early universe looked like? So basically going back in time, can we tell how the universe looked like? Extremely high dimensional inference problem. Now, this is what we refer to as field level inference. So you start from a observed galaxy distribution, a 3D point cloud of galaxy positions, and you try to infer the early universe, so the density fluctuations in the early universe, which we call the initial conditions in a simulation, a very, very high redshift, and then the overall composition of the universe, right, with the cosmological parameters that tell us the overall composition of the universe. Then you can forward simulate your observable, right? So we could run a simulation on those inferred initial conditions and composition of the universe and get basically like a digital twin of our universe, where the large scale structure will be where we actually see it. So usually what we do is we sample some random initial conditions that have the properties that we expect. And then we say, okay, we want to match the universe on average, right? But here, what we're advocating for is that we don't match the universe on average, but we actually match the universe that we observe. which is a much harder problem because obviously these initial conditions are very high dimensional. So let's say 10 to the 9 pixels that you want to infer so that you can sample something that looks like the universe that we observe at low redshift. So basically you're trying to constrain the evolution of structure as well, pixel by pixel, using the entire data set. So it's a much more challenging problem. And we want to get posteriors over this, right? Because there will be uncertainty on these initial conditions and uncertainty on these parameters, and we want to quantify that as well. But super interesting because what we call cosmic variance, or the fact that the logical structure could be varying, right? As you vary the initial conditions, will be hugely reduced by doing something like this. And you will actually, for instance, simulate where the clusters that we see around us should fall. Like the local universe should be very constrained by this kind of approach. And you have simulations that have actually the structure that we see around us. Now, these cosmological parameters that describe the overall properties of the universe are very low dimensional, let's say order of 10-ish, but the initial conditions are very high dimensional, order of 10 to the 9. So it becomes a much more complex problem than it was before, when we only cared about average properties of the universe. The observable is also very high dimensional, so that helps us definitely in terms of constraining power, but it makes the problem much more cumbersome. Now, why would we do this field level inference business? Well, so far, people have argued that this is the way to get optimal constraints. So if you want to learn about the average properties of the universe, actually doing field level inference is the way to guarantee that you'll have optimal constraints. Now, I'm going to argue that we don't really need to infer 10 to the 9 parameters to constrain 10, right? We don't really need to infer the random seed of the universe to constrain the average properties of the universe. In particular, now with machine learning, we really don't need to do that. Now, I think there's still interesting things that we can do by inferring initial conditions, but it's not to obtain optimal constraints. If you care about optimal constraints, what you can do is, first of all, compute the marginal likelihood. So usually the problem is that we can compute the likelihood of our observable given the initial conditions and the cosmological parameters. But what we care about is the marginal likelihood. So once we marginalize over these initial conditions. Now, this is extremely high dimensional. So the only way we can do this is by Monte Carlo sampling, which is super expensive, right? So this has been the approach so far to infer the initial conditions so that we can solve this marginalization problem. Now with machine learning, we don't actually have to do this because if we have samples from simulations where we vary the initial conditions and the cosmological parameters, we can learn a marginal likelihood. So the model can already learn to marginalize over initial conditions. And we'll talk a bit more about how we do this. The other option is to learn an optimal compression of our data set. So you can learn a neural network S that is compressing your observable, that is very high dimensional, into a lower dimensional space in such a way that your cosmological constraints are optimal. So you're basically kind of maximizing the mutual information between your summary statistics and your parameters. So this is a learning problem you can frame, and you can find this optimal summary statistic without having to marginalize over the initial conditions explicitly. Everything is happening implicitly by learning from samples. Now, how does this, we refer to this as explicit likelihood if we're actually learning a likelihood, or implicit likelihood if we're going to the posterior directly instead of learning the likelihood in between. Now, how does this look like in practice? So these are all generative models. And the idea is that you have some training set, so some samples. In this case, this is an example of the 2-moon problem. So it's a 2-dimensional example. Each point here is a training example, and it has 2 coordinates, x and y. And now the idea is that we want to learn a continuous probability distribution that is parameterized by some parameters phi. These are going to be the weights of our neural network that allows us to estimate the density of points at any given point, even at points that were not included in our training set, right? So that is the objective. Now, the most usual way to do this is by maximizing the likelihood of the training samples. So we go back to our training samples and we make sure that we find the neural network parameters that maximize the likelihood of having observed what we've seen. Now, this is not how we do it in very high dimensional problems because it gets very tricky to estimate likelihoods, but it is a proxy for this. So you're always trying to get something like maximize the likelihood of my training examples. Now, once you find your phi parameters that maximize your likelihood, you can do things like take your trained model and generate novel samples, right? So there's an example from human faces generated by AI. Another thing you can do is evaluate probabilities. So hopefully, if your model is well calibrated, so if it's working well, it should be able to tell you that this human face has a high probability of being observed, whereas a human with 3 legs has a low probability of being observed. So if we think about what we do with simulations, so simulations allow us to generate novel samples, right? So I can run my simulator with different initial conditions and change the parameters and generate a new sample, but my simulator doesn't know about the space of possibilities. So it can't tell me what is the probability of observing a given sample, right? So the generative model is acting both as a fast emulator of a simulation, but also as a likelihood model. So it can help us do inference, right? It can compute the probability of something having happened given some set of parameters. And we're going to take advantage of that to avoid summarization. So we can set constraints without actually having to summarize our data sets. Now, usually, I like to think about this problem as the problem of bridging 2 distributions. And this is a quote from Yang Song, that creating noise from data is easy, whereas creating data from noise is generative modeling. So usually the way we think about it is that we have some simple base distribution, x naught, here a Gaussian. So this is a one-dimensional problem. You have a Gaussian. And then you have a target distribution, x1, which is your data set distribution. You have samples from it, but you don't know its density. Now, what you can do is find a bridge between these 2 distributions, such that I can sample from the base distribution and follow this path into my target distribution, or I can get my samples and get the reverse path to evaluate the likelihood. The idea is that the base distribution is simple to sample from, but you can also evaluate the likelihood of it. That's why Gaussians are so popular, because we really know how to sample fast from them, but also evaluate their likelihood. And that's why most models actually start from noise. That's what this quote is getting to. They start from noise and go to your target distribution. Now, there's some details on how you build this bridge. It could be a stochastic bridge. This is what you see here in these SDE lines, right? So it's a stochastic differential equation that maps from your base distribution into your data distribution. Or it could be deterministic. So that would be the ODE formulation, the ordinary differential equation, which you just need to learn a velocity field, right? So that's very simple. You're basically parameterizing a velocity field that takes you from your base distribution to your target distribution by a neural network. And that will give you a continuity equation that allows you to predict the probability of your target data, right? So this is a very high level what a generative model is actually doing in 1D. But it works the same in higher dimensions. So it's very generalizable. And any type of data distribution. It could be a point cloud, it could be a galaxy image, and we'll see examples of that. Right, so this is an example of how you can learn the marginal likelihood. So you can vary the initial conditions of your simulations and the overall properties of the universe, what we call the cosmological parameters, and get examples of how your observable should look like. So these are some examples of the dark matter distribution in the universe generated by a generative model. So now you can start from this base distribution that is basically noise, and you've learned a velocity field that will take you to your target distribution. So you can generate new examples. So here we're varying the cosmological parameters and showing what the model predicts dark matter distribution should look like, kind of marginalized over the initial conditions. So you can sample the initial conditions. This is on very small scales, right? So 25 megaparsecs of range, because it was trained on hydro simulations that are very expensive to run on larger volumes, but it contains all the effect from baryonic physics. So this is looking at the total matter distribution in the universe at a resolution of 100 kiloparsec coverage. But you can do this for point clouds as well. So this is an example where we're trying to think about how this will look like for a galaxy point cloud, where each point here is a galaxy or a proxy for a galaxy. And the noising process here, what it does when you add noise is to make these galaxy positions noisier and noisier until they become a Gaussian distribution, like you see here, like a Gaussian blob. And now the model has to learn to reverse this process, so learn a velocity field that will allow you to reverse how these positions were noised. And you can use these models to evaluate likelihoods. That is something the simulator couldn't do, right? So now without summarizing my data set, I can tell you what is the likelihood of each one of these examples as a function of the cosmological parameters or some properties that you would like to constrain. And now I can sample this likelihood in any way I will sample a likelihood, right? To go to a posterior distribution and constrain my parameters without summarization. So you can get all the information that is there in the field and without explicitly sampling the initial conditions. So this is one approach. And it allows you obviously for very fast simulation, right? So you can generate these density fields in like about 6 seconds per simulation versus like 40 million CPU hours that would take to run an actual simulations. And they're still extremely accurate. Are there any questions or comments so far?
No, I think we're good.
Cool. Okay, so we can continue. Right, so that allows us to get the marginal posteriors by sampling what we call the neural likelihood, right? So we've learned a likelihood from our simulations, and now this likelihood is differential, so we can actually sample it quite fast. Also, because the parameters theta that we're interested in are kind of low dimensional, this is not too difficult. But the approach too would be, as I said, to learn a summary statistic that is optimal for a given task. So we do not need the sample index conditions to constrain our models optimally without summarization. Now, why I'm still interested in index conditions, we'll talk about in a minute. But I want to highlight why the differences between learning the likelihood versus the posterior. This is work that an entire Maduro student at the CFA has done with me on comparing this neural likelihood estimation, so these generative models to learn the likelihood, to this learning the optimal summary statistic compression. So here you can see how they work to predict a parameter like sigma 8, so something about the composition of the universe. So you have the true on the x-axis and the predicted on the y-axis. You can see that they both perform similarly, but maybe the likelihood model is working slightly better, but that's not the point here. The point is that if we take our density fields and add some Gaussian noise to them, so very little amount of noise, such as the power spectrum will not even change, what happens is that the posterior model becomes biased very quickly. So it becomes very non-robust, whereas the likelihood model is still working relatively well. If we add more noise to it, this is even more obvious, right? So these posterior models are really not robust at all. And we will never hope to capture all the details in our data set, right? So this is definitely something we should worry about. The fact that very small perturbations in our training distribution can cause huge shifts in the inferred parameters. Now, why is the likelihood model more robust instead? Well, I think a good example is a classification problem. So let's say that you're trying to classify animals, like cows, for instance. If you train the model to just directly classify whether a cow is present in an image, it would probably take advantage of things like, oh, there is grass. So what we call spurious correlations. So correlated variables that are not actually causation, but correlation. So if there is grass, I predict cow. Whereas if you train a generative model to generate images of animals given the class, so probability of image given cow, the model has to still learn what is a cow, right? So it still has to generate the shape of an entire cow in order to learn this probability distribution. So they're kind of more robust to these spurious correlations. And I think something similar is happening here. So learning the likelihood, even though is more challenging because X is much higher dimensional than theta in physical models. This is usually the case, right? In all of astrophysics. Usually your data distribution is more high dimensional than your physical parameter distribution. So it is harder to learn a likelihood, but in the end, it turns out to be more robust than learning the posterior directly. Right. So going back to why we want to infer the initial conditions. So okay, it's not to do optimal parameter constraints. We've already agreed that it's not necessary if you use generative models. But I will still say it's a super interesting thing to do. So the idea, again, going back, is that you have observed some distribution of density in the universe, usually through galaxies, but it could be through lensing or through other observables. And you want to infer the random seeds that give rise to the distribution we see today, jointly with the average composition of the universe, such that we can run simulation forwards that match our universe today. So why is this interesting? Well, first of all, because you reconstruct all latent variables. So all these variables that we can't directly observe, but we would love to use to learn different things about the universe, like the dark matter distribution. So if the universe was made of cold dark matter, how is it distributed? Can we infer, for instance, the distribution of filaments in the universe that we don't see directly through galaxy surveys? Then we can use that distribution to maybe correlate it with, is there any emission coming from dark matter that is very weak, but we can find if we know where the filaments are. This is one example, but obviously this allows you to constrain entire formation history. So can we say something about the formation history of objects around us? Is it very constrained by your data? Is it not very constrained? Or peculiar velocities. So in galaxy surveys, we see where galaxies are, but it's actually contaminated by the fact that they have some peculiar velocity. So we measure their redshift, but we can't directly translate it into distances because they also are moving respect to us. And that contaminates the signal, but here we could reconstruct the peculiar velocities and actually know where the galaxies are, or at least do with some certainty, right? We could sample potential galaxy distributions without this effect of peculiar velocities. So these are some interesting things we can do by reconstructing. But also, I think something very interesting is to see whether we can actually say something about inflation in a model-independent way. So usually what we do is we assume some model of inflation, unconstrained with observations. But here we could ask the question of, can we find some signal that is model-independent in these reconstructed initial conditions? Now, this has a question mark because we will train our model assuming some model of inflation. So it all depends on how strong the likelihood is versus the prior, right? So it's unclear whether this will actually work for the current generation of galaxy surveys, but it's an interesting question. And what I'm very excited about is the fact that these models can be very predictive. So if you're inferring both the initial conditions and the underlying overall composition of the universe, now you can ask questions like, okay, how does my reconstructed density field compare to lensing over the same footprint or correlations with the cosmic microwave background? Now without cosmic variance, right? Because you just inferred the initial conditions. So it becomes very predictive and you can play this cross-validation game to validate that what you've done is actually correct, which is a challenge with machine learning models, right? How do we validate the inference that we've done? But here we actually have a pathways to validating that what the model has learned is actually correct. So this goes back to the example I showed you from chemistry, right? Where you had a model that was allowed to be wrong because you could validate it in the lab. So here it is similar. You kind of can get things wrong, but you can validate whether that has happened or not. And that's very important, right? To have some safeguards on whether we can validate what we're doing. So still, a super interesting thing to do to infer the initial conditions, just a very hard problem. Another interesting avenue is whether we can use those inferred initial conditions to learn about subgrid physics, right? So about what's happening on very small scales, given that now we have a constrained simulation that looks like our universe, or can we learn something about the systematics that we know are present in our surveys, etc. But again, this is a bit more experimental. Now, what we've been working on is comparing simulation-based inference, so these generative model approaches, to explicitly sampling the initial conditions as people were doing in the past. So we had an example where we had a very simple gravity model, so dark matter only, particle mesh, so very fast, and we assumed a Gaussian likelihood. So here we had some observation, dark matter only density field. And we were trying to sample the posterior over initial conditions and parameters given the observation using generative models. So here you can see an example of the constraints on the cosmological parameters of the overall composition of the universe coming from the generative model in purple, or explicitly sampling the likelihood. So this is the Hamiltonian Monte Carlo. So this is kind of the ground truth for this particular example in gray. And they're super similar, right? So the model was working well in terms of parameter of recovery. Now, what's interesting is that in reality, the likelihood is not Gaussian. So the HMC approach, so sampling the likelihood explicitly, is actually not feasible because we know the likelihood is not Gaussian. So this model can overcome this by using simulations to inform the likelihood instead, right? Learning the likelihood from simulations directly, not assuming that it's Gaussian. Also, the forward model is not necessarily differentiable. If you think about a hydro sim, it's very hard to make it differentiable. So these sampling methods that take advantage of knowing the gradients, like Hamiltonian Monte Carlo, are really necessary if you want to solve this high-dimensional inference problem. So if you don't have gradients, you really can't constrain 10 to the 9 parameters. It's impossible, right? So the generative model approach does not require the forward model to be differentiable. And it's amortized, meaning once we train it, you give me any final density field and I can produce initial conditions very, very fast. Whereas for the sampling methods, you have to run an entire HMC chain every time you want to get constrained on your initial conditions. So for testing, this becomes a much more rapid to iterate over setup. It's much more convenient, let's say. Now, how did it look like? So here you have an example from some true initial conditions on a small box and some observed density field. The idea is that now we can sample from this posterior really fast with our model and sample some reconstructed initial conditions. So here you see different samples, right? Now we can run the full model, so our very cheap dark matter only simulation on top, and see whether the structure will actually fall what we will expect, right? So this is what you see, these big clusters forming in the bright regions, where there's a lot of empty space in a void region. So the model is really finding the initial conditions that will reproduce the final field. Now there is a lot of dancing around, right? So these structures are kind of moving one pixel away. So the model is not perfect. It should definitely pinpoint these very sharp structures. But small changes in the initial conditions can lead to large deviations on the final conditions. So that's something that we're thinking about. How do we correct these models to avoid these small mismatches? But it's still already working really well for a high dimensional problem. Right, so, sorry, there's a comment in the chat. Right, we'll go back to it in a minute. Yeah. So how will this look like for, let's say, DESI, for instance, the largest survey that we have, the largest 3D map of galaxies that we have available to us? Well, doing this for DESI is not straightforward for different reasons. First of all, because there's a lot we need to full model in terms of what is it that the survey actually measures. We don't just see the 3D galaxy distribution of all galaxies in the universe. The survey selects some galaxies based on their colors, for instance. So this is something you would like to full model. And it has some systematics, like the fact that the way they measure spectra is constrained by some robotic arms. So you have some fibers that are capturing light coming from these galaxies, but the robotic arms cannot move everywhere. So if you have a very dense region of the universe, you have to make some assumptions that you won't be able to observe all the galaxies. You'll be losing some of them. And this is a density-dependent effect, so it's actually important. So all these things are things we're working on how to actually implement this in our simulations to make them as realistic as possible. Now, one of the big problems is that we don't actually understand how galaxies form. So we observe the distribution of galaxies, but even though we think we understand the distribution of dark matter relatively well, or we can simulate it relatively accurately, that's not true for galaxies. So we know that galaxies populate, are born in this dark matter cosmic web that looks like very filamentary and full of nodes, but we don't actually understand exactly how that happens. So full modeling this is actually challenging. So putting galaxies in our simulations is very challenging. And it is very hard to scale up in volume, right? To go to simulations that have the volume of DESI, for instance. So DESI year one, so the first year of observations, is already much larger than any simulation we have for training our models. So this is definitely a challenge. Now, we understand how large scales work with perturbation theory, so maybe there are avenues in which we can combine simulations on small scales, perturbation theory, and large scales, but this is all experimental, right? So there's a lot of things we need to, lots of future research for you guys to work on as well. But there is a path towards doing this for DESI. That is very exciting. Now, the main issue, as I said, is galaxy formation, right? So how do galaxies form? And we have different ways in which we can connect the dark matter distribution to galaxies, more physically based or more empirical. There's a whole spectra. Now, in my opinion, the most interesting one is still hydrodynamical simulations, where we try to self-consistently evolve dark matter and gas that forms the stars and galaxies, because that will give us self-consistent predictions across different observables and different wavelengths, which is very hard to get with any of the empirical models. You're really constraining the same physics, right? How gas collapses into stars and forms galaxies with different observables. And this is exciting because over the next few years, we're going to get really good data about different wavelengths. So how X-rays, for instance, constrain the way that gas is distributed in clusters, or the gas density profiles in clusters, but also the Sunyaev-Sadovich effect from the cosmic microwave background that allows us to probe the density of hot electrons in big objects, but also the integrated electron density along the line of sight, or galaxy properties from galaxy surveys that we usually just throw away, like the star formation histories, or fast radio bursts that will probe the integrated electron density along the line of sight. So all these things are very correlated to how gas collapses into stars and forms galaxies. And really looking at it as a more holistic picture will help us constrain it and improve the way we do cosmology as well. Because otherwise, if we come up with very flexible models, we end up losing a lot of the information that we were originally after. So in my opinion, hydrosims, even though they have shortcomings, are the way to go right now about this problem. Now, the problem is that doing hydro at scale is very difficult, right? So usually we have very small volume hydro simulations, let's say 25 milliparsecs of range. So that's extremely small for cosmology, but we want to make predictions on very large volumes, density volumes. So what we've been working on is, okay, if we start with particle mesh for gravity, so this is an approximate version of gravity is where you lose the smaller scale information, but it's very fast, and we can run very large volumes without issues. We can start from particle mesh and now take some hydro simulations. So this is from the CAML suite, where the subgrid physics, so the way feedback works is being varied. Now we can predict some baryonic properties, like the galaxy distribution, given the dark matter distribution generated with particle mesh, cosmological parameters, and some measure of feedback. And then we can generate gas properties like density and temperature trained on those small volumes, but upscaling to much larger volumes. But the same for the galaxy distribution, right? So we can really train on small volumes and then do inference on much, much larger volumes. So it's a way to make much larger hydro simulations that we could ever resolve. So the current model that we presented at this workshop is optimized for the Lyman alpha forest for about Redshift 2. And it's extremely fast, right? So you can run in 7 GPU minutes. You get a 50 milliparsec simulation, for instance. So we used it to take the CAML's volumes of 25, train it on there, and then deploy it on much larger volumes of 50 milliparsecs. So this is a path forward to using hydro simulations in this whole program of reconstructing the initial conditions. And I'm realizing that I'm doing extremely bad in time. So I'm gonna wrap up here to give you a chance to ask questions and make sure that we can have some discussion by directly jumping to conclusions. Yeah, it was. So basically, we made it through the first point of this talk and maybe half of the other one on how generative models can really help us solve some of these very interesting high-dimensional inference problems that are interesting for different reasons, but in particular allow us to validate that the machine learning model has actually done a good job, which is extremely important for future surveys. And I've shown like a path forward to using generative models also to upscale current very low volume simulations into something that is useful for the data analysis that we have to tackle over the next few years. Now, sadly, I didn't have any time to go into the role that language models can play in science, but very happy to discuss with people that are interested. And the last thing I wanted to say is that I'll be joining NYU next year, New York University, as faculty. And if you're interested in postdocs, or if people are interested in applying for PhDs at the intersection of ML and Astro, yeah, please send an email. I'm very happy to chat about it. Thank you.
Very much. So just on the last point, LLMs in science, we've had 2 previous speakers. Ioana Chuka and Yuan Sinting, who in previous talks have talked about very similar things. So if anybody online or in person is interested in that topic, go to our YouTube channel. You can see these recordings. You can hear what's going to take place in astronomy in this area, at least like 6 months ago, a year. I'm sure it's all changed since then. So what we normally do is take questions from the room, then online, but I can see that we have one online already. So I'll just read that out. So the question is, can generative AI really help in training with what is available, e.g. matter, simulates to see something that's invisible like dark matter.
Right. Yeah, for sure. It can help in very different ways. So something we've done in the past is showing that you can train models in a small scale hydro simulations, like the camel simulations, to undo the mapping between galaxies and dark matter. So basically, given some galaxy distribution, you could sample the posterior of the possible dark matter distributions. There is some degeneracy, right? Because there's a lot you don't observe. So what you can constrain is some properties of the dark matter cosmic web given the galaxies that we see. And then you can use that for cross correlations with other probes, etc., and learn other things. But yeah, you can do things like that. I think that's what I understand from that question. But it's a bit of a general question, so I'm not sure if I answered the question I took.
Okay, well, I actually have like a relevant sort of provocative question to that. So we're talking about the data that we have, the techniques that we have, the compute and the simulations. To what extent, though, are we bringing in our own biases by incorporating simulations? So, like the probably canonical example would be simulations which include dark matter as opposed to some kind of modified gravity. Now, are we not kind of bringing in too many prior assumptions by using simulations, or at least we can guard against that?
Yeah, no, I think that's a great question. My approach here is so far we don't have any compelling evidence of beyond lambda CDM physics. So my opinion, the road right now is to really stress test lambda CDM. I think that's where simulations are going to be extremely useful, right? So let's say, okay, if lambda CDM were true, how well can we reproduce observations to the precision of the data that we have, which is extremely good right now. Now, if we see it fail, then things get interesting. But so far, that we haven't had evidence of that. So DESI right now is the closest we get, but it's still pretty weak, right? So I would say first, let's stress test lambda CDM and see if it breaks. And after that, think about how do we scale this to what interesting physical theories. And that's kind of where I wanted to get with the role of LLMs. I can briefly show you something where if you think about sorry, let me go back. The scientific method, where most of what I've talked about today is how do we go from testable predictions, so how we use high dimensional data to test our predictions, right? So in particular, how will we use high dimensional data to stress test lambda CDM, right? But now there's the interesting question of whether ML can help us actually expand the hypothesis space, right? So, okay, once we see it fail, how do we come up with alternative scenarios that might actually explain the data? And can the models themselves help us implement this new physics into simulations in a more automated way, right? So that we could automate the art of theory building, let's say, right? So, okay, you see something break, you ask the model to come up with a hypothesis that could explain it, it implements it in a simulation code and gets constraints. And we did a very small scale experiment of how this could work with the cosmic microwave background and the BO DESI data, right? Where all you need is to modify the code like class. We call that a simulation code in this case, right? But you could see how this could generalize to larger and larger problems. Now, we're not still there where the models are good at this, but it is still very useful to evaluate how they fail. That's my perspective.
I suppose the risk with that is it becomes too circular, kind of too inward looking. So you have these like new hypotheses, but they have to be based on what people have already said. So maybe it could be the case that you connect two areas which haven't been connected before, and you can make a leap there. But I don't know, like if you trained you train a model like this on all the papers up until like 1910, would it come up with relativity? Do we still need that kind of creative spark, presumably?
Right. And the answer is right now, I'm sure not. But I think the question is how do we should look at these models as the pre-training, right? So, okay, now we have a pre-trained model that is extremely capable of doing different things like implementing code, but it still doesn't seem quite creative, right? And the question is, how do we reinforcement learn a physicist, right? Okay, so let's see these as pre-training. The pre-training might not be that groundbreaking for science, but what can we do on top of that to make them more creative? So how do we build an iterative process in which the model is improving its own hypothesis? I think that is the question right now. Like, how do we use these pre-trained models in interesting ways that will
Yeah,
involve more than just the pre-training, right? The model needs to be able to explore the world, play with it, etc.
yeah, I think it'd be interesting to see if you can make them so that they come up with creative hypotheses that aren't necessarily penalized for having a low chance of being correct. You sort of want to have these sort of one in a million ideas, which nobody thought was going to be right, but actually kind of turned out to be correct, and not penalizing the model ahead of time for taking those kind of risks.
Exactly. Yeah. How do you set up a problem like that with a pre-trained model that is already pre-capable?
Interesting one. Okay, so sorry, I've dominated all the questions. Do you have any questions from the room?
Would well, maybe it's almost too early for, but would this kind of observation help, like, well, narrow down any kind of model-specific dark matter? So, like, because I know there's a lot of different models and a lot of things. Does this help constrain what possible things we have?
Yeah, for sure. So that is the ultimate goal, right? So, well, first of all, yes, I said, I think that the first element is to see if cold dark matter breaks. So that's still unclear, right? We don't have any like observational evidence that is like, okay, we cannot explain the data that we have. Usually, I think because we summarize the data in ways that is very lossy. So that's why I think step one is to stress test cold dark matter. Then once you see it break in some regimes, then you can start thinking about what are the relevant hypotheses that we should test that is not cold dark matter. Now, one of the big problems with dark matter is that we know that small scales are very constraining, but that's also where baryons are most uncertain. So I think thinking about ways in which dark matter has specific signatures that are not seen in baryons, and this can be a representation learning problem, right? How do we find a representation of small physics that splits into what the baryons are doing and what dark matter is doing in ways that are unique, right? So we can blame the baryons for certain things, but it's only things that could be explained by dark matter physics. But it is a very challenging problem, right, to distinguish these two, because the uncertainty in baryonic physics is just way too large, sadly.
So to kind of play devil's advocate, could you, instead of starting from a position of the CDM, could you start from a position of, say, like self-interacting dark matter to some extent? And presumably you'd be in the same position where, yeah, on kind of bigger scales it looks okay, but the baryonic physics is still kind of constraining.
Right, so here you're going for the Occam's razor, right? What is the simplest explanation of the observations we have? And currently it is true that cold dark matter would be the simplest explanation in a way, right? We still don't have a candidate, like a particle physics candidate for it, but it's still the simplest way to think about it, right? It's cold, it doesn't interact very much, like it is the simplest. Whereas when you add self-interacting dark matter, you're adding a layer of complexity that you'd want to justify by it has unique signatures that could only be explained by self-interacting dark matter. And this is what we don't have currently. Unique signatures are really not explained by cold dark matter.
Okay, any more questions from the room? Or if not, online, put your hand up or drop a message into the chat. Okay, well, I can go to another one of my 10 or so questions up until we get to 4 o'clock. So you started off by showing these world models and the amount of progress you've seen in like the last 6 months or so. We've also seen Nobel Prizes in chemistry for people from DeepMind. The kind of advances that you can have using these kind of techniques. Do you think that we're going to see similar advances in astronomy and cosmology, like in the near future, say with these big surveys coming online, increased skills coming through the pipeline, thanks to CBTs like yours and ours, obviously? Do you think are we in that kind of regime where we're going to see like big change very quickly, or is it still going to be pretty incremental?
But I really hope so, right? But it is still a hope. Like, of course, there's no guarantees, right? I think so far the biggest advances in science have happened in biology. And this is something that people say, right? That sometimes you could think about it as like in the way that maths is the language of physics, maybe machine learning could be the language of biology. So it's that these systems are so complex that we really didn't have a mathematical description of them, or it was really impossible to come up with an accurate mathematical description of it. Whereas it is true in astrophysics, like the fact that lambda CDM works as well as we see it work with like less than 10 parameters is insane, right? So we definitely work in a different regime where it's less obvious that things would be as revolutionary. At the same time, given the scale of the data sets that are coming in, I really think there is a huge potential for discovering interesting physics. But yeah, this is definitely an open question, and we'll have to show it over the next few years.
Great. Okay, I see we've got a question from Joe online. So yeah, go ahead, Joe.
Hi, thanks for the talk. It was very nice. Is there, sorry if you said this and I missed it, is there like a dynamical system part to your generating a universe? Because I do some work with Monte Carlo chains and with variation autoencoders, and I'm finding a huge problem with the dimensionality of the bottleneck in the middle, and ergodicity, being able to sample the whole space. Are these related to your work?
Right. You mean like what are the guarantees that you'll be able to sample the whole space and you don't get stuck in like different regions?
Yeah, if not in one jump, then maybe a few, but yeah.
Right. So yeah, these are always problems, right, for generative models as well. In the same way that if you have a multimodal distribution, it is hard to sample it with, let's say, Monte Carlo sampling, like Hamilton and Monte Carlo, etc. You can get stuck in regions of the parameter space. But these end up being not as bad for generative models, because during training, you're jumping a lot. So it can still happen that you collapse to a mode, but because you're not like sampling sequentially, like a Monte Carlo chain, right? These tend to be less severe.
Okay.
Like you're more like the problem is that you can have correlated errors in all your training set, generated training sets. So let's say that the model learns some wrong small scales and there is a bias, right? Then all your samples will be biased in the same way. Whereas if you know the true likelihood and you sample it, you're not going to have a bias. You could still have that the samples are too correlated, but they won't have a bias. Whereas here, although the samples are independent, they could still have correlated biases. So it is a bit weird.
Sure.
Like it comes with its own issues, but they're different.
Okay, thank you very much.
Okay, I think we'll finish it there. So let's thank our speaker one last time.
Thank you very much for having me. Good luck with your PhDs.
So we're back next month on the 11th of November with Danny Water, who's Marie Curie Fellow at the University of Edinburgh. And he'll be talking about foundation models for Milky Way signs for something like eye data and stuff like that. So if anybody was to accuse me of being strongly biased, they would not be wrong. But we're getting back to particle physics in December. So I hope to see you then.
Thank you.
Okay, thanks, Carol.